All right, let's dive into quantum computing today. We'll be looking at some fascinating articles from Scientific American.
Sounds good.
Quantum computers always seem so futuristic and mysterious, right?
Right.
But we're going to demystify them today.
Okay, sounds fun.
So what are they? How are they different from our everyday computers? And why should we even care?
Yeah, those are good questions.
Yeah.
It's a field with so much potential,
Mm,
but it can be tough to understand.
totally. So first things first, what does a quantum computer even look like?
Right.
I picture a laptop,
Yeah.
or a desktop. But Scientific American describes something completely different?
Oh, yeah, they do. Think more like an intricate chandelier
Okay.
with delicate wiring, layers and layers of it.
Mm-hmm.
And the whole thing is encased in this massive super refrigerator.
Whoa. Okay, that's not your average laptop.
Not at all, no.
So why so cold?
Well, that super refrigerator
Yeah.
is bringing the quantum chip down to near absolute zero, colder than outer space. Yeah. And it has to be that cold for the circuits to exhibit these really unique quantum properties.
Okay, so we've got our super cooled chandelier, but how does it compute?
Right.
It's not just ones and zeros, is it? Like our regular computers.
No, it's not. See, classical computers, they use bits,
Right.
which can be a 0 or a 1, like an on or off switch, basically.
Okay, makes sense.
Quantum computers, on the other hand, use qubits. And that's where things get interesting.
Okay, so qubits, how are they different?
So instead of just being on or off, a qubit can be in a state called superposition.
All right, superposition. Here's where I start to get lost. So it's not just 0 or 1. It can be both at the same time.
You got it. It's like having a single computer processor that can run multiple programs all at once. It's like a massive parallel processing system all in one unit.
Okay, so if a qubit can be in multiple states at once, does that mean it can solve any problem way faster than a classical computer?
Well, it's not really about speed. It's more about tackling specific types of problems in a fundamentally different way.
Okay, so it's not just faster. It's doing something different.
Exactly. They excel at certain types of problems, particularly ones involving complex simulations and optimizations.
I see. So how does this parallel processing with qubits work? What's the mechanism behind it?
It all boils down to the mind-boggling principles of quantum mechanics. Qubits can exist in multiple states simultaneously, allowing them to explore numerous possibilities at once.
Hmm.
This leads to an exponential increase in computational power. 2 qubits can represent 4 values simultaneously. But get this, with 20 qubits, you're talking about over 1 million possible values at once.
Whoa, that's incredible. But I remember reading about another concept too, entanglement.
Oh yeah, entanglement.
How does that fit into all this?
Entanglement is key to quantum computing.
Okay.
Imagine 2 qubits linked together.
Mm-hmm.
Even if you separate them by a huge distance, they share the same fate. Change the state of one. The other changes instantly as well.
It's like they're telepathically connected or something.
You can say that. It's almost like having a network of processors that are intrinsically linked and can communicate instantaneously.
Wow. So what does this entanglement mean for computing power?
It takes the potential to a whole other level.
Okay, so we have these super powerful qubits that explore tons of possibilities at once, and they're linked in the speaky way.
Right.
But what does it all mean in the real world? What are the implications of this power?
Well, let's take prime numbers, for example.
Prime numbers.
Those numbers only divisible by one in themselves.
Right, for math class. But what do they have to do with anything?
Well, they play a huge role in encryption. Think about how your online banking information is kept secure.
Okay, yeah.
That's partly thanks to prime numbers. It's really difficult to factor large numbers into their prime components. For classical computers, I mean.
So that's why our info is safe. Because of prime numbers.
Exactly. It takes classical computers forever to factor large numbers, which makes encryption secure. But then there's this algorithm, Shor's algorithm. And it could factor these numbers much more efficiently on a quantum computer.
Wait, so a quantum computer could crack the codes that protect our online information?
Theoretically, yeah. That's the power of Shor's algorithm.
Hmm.
It highlights the potential of quantum computers to tackle problems that are practically impossible for even the most powerful classical computers.
So they might not be replacing our laptops anytime soon, but they could break encryption.
Right. And this isn't just theory either. IBM actually built a quantum computer to try this out.
They did? When?
Back in 2001.
Wow, a while ago.
It was a rudimentary quantum computer, only 7 qubits. They use it to demonstrate Shor's algorithm, They factored the number 15 into its prime factors, 3 and 5.
So not exactly breaking into the world's banking systems yet.
No, not quite. It was more a proof of concept. But it was a crucial step. It showed that the algorithm could work in practice.
That's still pretty amazing.
Yeah.
And I imagine building and controlling these machines comes with its own set of challenges, right?
You bet.
Yeah.
One of the biggest is the fragility of quantum states.
Okay.
They're susceptible to noise and interference from the environment. This leads to decoherence, which basically disrupts the superposition and entanglement.
And that causes errors.
Exactly.
So it's like you're trying to build a house of cards on a shaky table. Any little disturbance could ruin everything.
Perfect analogy. And that's a major obstacle in building large-scale, stable quantum computers.
So what are researchers doing to tackle decoherence and stabilize these systems?
A few things. One approach is error correction,
Okay.
which involves using additional qubits to build redundancy and correct errors.
So like backup qubits.
Yeah, like having extra qubits to step in if things start to go wrong.
Makes sense. What else?
Well, another approach is developing algorithms that are more tolerant of errors, basically finding ways to compute even with noise in the system.
Interesting.
And then there's a lot of buzz about using more exotic qubits, like topological particles.
Topological particles, huh? That sounds like we're getting into some serious physics territory. Is that still theoretical?
It is. Harnessing them for quantum computing is a long-term goal, but it's a hot area of research.
It seems like we're still in the early stages. There are challenges, but also huge milestones, right?
Definitely.
Like quantum supremacy.
Right. Google made headlines a few years back with their Sycamore quantum computer. They claimed to have achieved quantum supremacy,
Meaning?
meaning they performed a task that would be practically impossible for even the most powerful classical computer.
What task?
With a complex simulation involving a quantum random number generator.
Okay.
They claimed it would take a classical supercomputer 10,000 years. Sycamore did it in minutes.
10,000 years versus a few minutes. Wow, that's a huge difference. So does that mean they definitively proved quantum supremacy?
Well, it was a huge achievement, but there was some debate. IBM argued that their classical supercomputers could have done the same task much faster.
So still some competition in the field.
Always.
It sounds like we're in this era where quantum computers are showing their potential, even if they're not taking over the world just yet.
Right.
But if Sycamore is an example of this super-cooled chandelier model, are there other ways to build these things?
Yeah, there are. That model, using superconducting circuits, is definitely a front-runner. Google and IBM are really focused on it. But another method uses trapped ions.
Trapped ions, what are those?
Charged atoms, basically. They're trapped in electric fields.
So they use individual atoms as qubits.
Exactly. Held in place by these carefully crafted electric fields, almost like they're suspended in midair.
That sounds so precise. What are the advantages over superconducting circuits?
Well, trapped ions are less susceptible to noise from the environment.
So less decoherence.
Right. They're inherently more stable than those superconducting circuits.
So it seems like each approach has its own pros and cons.
For sure.
It'll be interesting to see which technology becomes dominant. Or maybe we'll end up with a mix of different quantum computing platforms, each good for certain tasks.
That's a real possibility.
It's early days, lots of unknowns,
Yeah, it's still early.
which is what makes it so exciting. We're at the beginning of a new era of computing with vast implications. We talked about encryption. But what are some other areas where quantum computers could have a real impact?
One area with immense potential is drug discovery and materials science.
So.
Imagine being able to simulate the behavior of molecules with incredible precision. You could design new drugs and materials with specific properties.
So instead of trial and error in the lab, we could design these things from the ground up using quantum computers.
Exactly.
Wow. Any other fields? What about things like climate change? Could quantum computers help there?
Oh, absolutely. They could be instrumental in developing new energy sources, optimizing energy grids, even capturing carbon from the atmosphere.
Wow. So it's not just about making things faster. It's about enabling us to tackle problems that are currently unsolvable.
Exactly. It's about pushing the boundaries of what's possible.
And this is where it gets interesting, right? As we develop more powerful quantum computers, we're going to face problems we haven't even thought of yet.
Probably.
The nature of computation itself could evolve.
It could. It really could.
Exciting and a bit daunting. Makes you wonder what the world will look like when these machines become more commonplace. Will we see a quantum computer on every desk?
That's unlikely. at least not anytime soon.
Why not?
Well, they're not meant to replace our laptops or smartphones.
So more like specialized tools.
Yes. Think of them as powerful instruments for researchers and scientists. They'll drive breakthroughs in fields like medicine, energy, materials science.
Okay, so this quantum revolution isn't just about incremental improvements. It's about unlocking entirely new realms of possibility.
Exactly.
And that's why it's so important to understand the fundamentals of quantum computing.
I agree.
It's a new way of thinking about information and computation.
It is.
It's definitely a mental stretch, but fascinating. Before we continue, let's recap what we've learned. What stands out to you?
Yeah, good idea. We've covered a lot. We
Yeah.
started by looking at the physical appearance of these machines, the super-cooled chandelier, as we called it.
Right.
And we talked about why that extreme cooling is necessary.
We also delved into the heart of quantum computing, qubits, superposition, and entanglement.
Right, those are central to their power,
And we saw how these concepts translate into real-world potential.
like with Shor's algorithm.
Right, and the possibility of cracking encryption, which has big implications for online security. We also talked about the debate about quantum supremacy and Google's Sycamore experiment.
Yeah, groundbreaking stuff, but hasn't fully settled the argument.
And we've just started to touch on the vast applications beyond encryption.
Revolutionizing drug discovery, materials science, tackling climate change, potentially even solving problems we haven't even thought of yet.
It's a lot to process, but hopefully it paints a picture of how revolutionary this technology could be. And we've only just scratched the surface. There's so much more to explore.
Absolutely. Let's keep going. It's funny, we started talking about quantum computers as these super complex machines,
Yeah.
almost otherworldly. But it seems like the really quantum part, it's not just the technology.
I know what you mean. It challenges how we think about how things work, right?
Yeah, like our brains are wired for cause and effect.
Right.
And then quantum mechanics comes in and throws all that out the window.
It really does. It's like we want yes or no answers, but quantum mechanics is all about maybe.
Exactly. Uncertainty and probability, that's the name of the game. It's a particle being in multiple states at once. It's things being connected across huge distances, stuff that just doesn't make sense in our normal way of thinking.
Yeah. And it's not just theory anymore, right? We're seeing these principles actually show up in the real world.
Right. Think about it. We've been using classical physics to understand and control the world for centuries. And now we're figuring out how to use quantum mechanics to do computations in this totally new way.
It's like we found a secret language of the universe, almost.
It is, kind of, a language that lets us tap into this level of complexity we never thought possible.
And it's still so early, too. Makes you wonder what quantum computing will be able to do in the future. What kind of applications will we come up with?
Yeah, it's hard to imagine. New ways to get energy, maybe, or design materials that have never existed before. We might even be able to simulate the human brain really accurately.
Wow. And the implications go way beyond just science and technology, don't they?
Absolutely.
Yeah.
Finance, communication, the arts, even. Quantum computing could change everything.
It really could. It makes you realize we're in a time of incredible change. And understanding this stuff, this quantum computing, it's becoming more and more important.
For sure. If you want to keep up with how the world is changing, you got to understand this new way of thinking.
It is like learning a new language almost. The language of the future.
And anyone can learn it. You don't have to be a physicist.
Right.
Anyone can dive into this world if they're curious enough.
I like that. So, to kind of wrap up this part of our deep dive, what are some key takeaways for our listener?
I think the main thing is quantum computing isn't just about speed.
Yeah.
It's a whole different way of thinking about computation.
Using quantum mechanics to solve problems we can't solve right now.
Right. Problems like cracking encryption, designing new drugs, tackling climate change.
There's many different fields.
It changed so much about our lives.
It's a lot to think about, but hopefully it's got our listener thinking about the possibilities. You know, it's amazing to think back to the start of our deep dive. We were talking about these elaborate quantum computers, almost like something out of science fiction.
Right.
But now, looking at the ideas behind them, superposition, entanglement,
Yeah.
it's clear that the really quantum part isn't the technology itself, it's the way of thinking.
It's a whole different way of seeing the world, yeah.
It challenges how we see reality. We're used to cause and effect, and then quantum mechanics is like, wait a minute.
It throws a wrench in the works. All those neat, predictable laws of physics we rely on,
Right.
they kind of go out the window at the quantum level.
It's like our brains want a clear yes or no, but quantum mechanics says, maybe, could be both, could be neither.
It's all about possibilities, probabilities,
Mm.
particles in multiple states at once, connections across vast distances. It's weird.
It's definitely a shift from how we normally think. And it's not just a theory anymore either. We're seeing these principles play out as we build quantum computers.
It's amazing, isn't it? For centuries, it was classical physics, the physics of everyday life.
Yeah.
And that's what we use to understand and control the world around us.
Mm-hmm.
But now, we're learning to harness quantum mechanics, this whole new set of rules. And we're using it to do computations.
It's like we've discovered this secret language the universe uses.
Yeah.
A language that lets us tap into a complexity we never thought possible before.
And it changes everything. Not just in terms of technology, but in how we see our relationship with the universe.
It's exciting, but also kind of intimidating, right?
Oh, for sure.
We've only just scratched the surface of quantum computing. Who knows what we'll be able to do with it in the future?
It's almost impossible to imagine. Think about it. New ways to generate energy, maybe even solve the energy crisis, or materials that have never existed before. Stuff that's stronger than steel, but lighter than plastic.
Right. And what about simulating the human brain? If we could do that accurately, who knows what we could learn?
It could revolutionize how we understand consciousness. It's mind-blowing.
And it goes beyond science, too, right? Quantum computing could change finance, communication, even art.
Yeah, it has the potential to change our whole society, things we can't even picture right now.
It's a time of incredible change, that's for sure. And understanding this stuff, this quantum stuff, it's more important than ever.
Absolutely. It's the key to navigating the future. You want to be prepared for what's coming. Learn about quantum computing.
It's like the essential skill for the 21st century, like learning a new language, the language of the future.
That's a great way to put it. And it's not just for scientists and experts.
Right.
Anyone can learn this stuff if they're interested enough. You gotta be curious, be willing to dive in.
Well, I think we've given our listener a lot to think about today. We demystified some of the basics, talked about the potential, even touched on some of the philosophical stuff,
Right.
But more than anything, I hope we've sparked some excitement about all this, about what quantum computing could mean for the future.
Me too. The quantum revolution is just getting started, and who knows what amazing things are going to happen.
Exactly. And maybe our listener will be part of it. So to all you curious minds out there, keep asking questions, keep exploring. The quantum world is waiting.
That's it. Until next time.